Picture this, a single, infinitely dense point containing all the matter and energy in existence, suddenly erupting with a force so immense that it created the entire universe as we know it. This is not science fiction, it's the story of the Big Bang, the monumental event that set the stage for everything we see around us today. But did you know that this incredible story didn't stop there? Cosmic inflation, a rapid expansion right after the Big Bang, transformed the universe from chaos into the beautifully structured place we observe now. In this video, we're about to embark on a mind-blowing journey through 25 incredible discoveries that scientists have uncovered about these two fundamental cosmic events. From the groundbreaking observations of Edwin Hubble to the stunning insights provided by modern satellites like Planck, each discovery adds a new layer to our understanding of how the universe came to be. We'll explore everything from the cosmic microwave background radiation to the mysterious role of dark energy, and even venture into speculative ideas like eternal inflation and the multiverse. So, whether you're a die-hard space enthusiast or just someone who's ever looked up at the stars and wondered how it all began, this video is for you. Keep watching, and together we'll unravel the secrets of the cosmos, one discovery at a time. Let's kick things off by exploring the very foundation of the Big Bang theory, the first piece of evidence that made scientists reconsider how the universe began. The story begins with Edwin Hubble, a trailblazing astronomer whose work in the early 20th century forever changed our understanding of the cosmos. In the late 1920s, Hubble made a groundbreaking observation: nearly all galaxies are moving away from us. This wasn't just a random finding, it pointed to a profound truth about the universe itself. Hubble's discovery was based on a phenomenon called redshift. When light from distant galaxies travels to Earth, its wavelength stretches as the universe expands. This stretching shifts the light toward the red end of the spectrum, much like how the sound of a speeding car changes pitch as it moves away from you. By analyzing the light from galaxies, Hubble noticed that the farther a galaxy was, the more its light was redshifted. This meant that galaxies weren't just drifting apart, they were accelerating away from each other at incredible speeds. What does this tell us? Well, if everything is moving apart now, it implies that the universe must have been much smaller in the past. This led to the revolutionary idea that the universe had a beginning, a single point from which it all began to expand. Hubble's work provided the first concrete evidence for the concept of an expanding universe, laying the groundwork for the Big Bang theory as we know it today. To visualize this, think of the universe like a balloon being inflated. As the balloon expands, dots drawn on its surface move farther apart from each other, just like galaxies in the universe. This simple yet powerful analogy helps us grasp the enormity of what Hubble uncovered. And it all started with his groundbreaking observations of galaxy redshifts, proving that the universe was not static but dynamic, a place filled with motion and evolution. With this discovery, we took our first step toward understanding how the universe came to be. Next, we'll dive deeper into the layers of evidence that continue to support this incredible theory. Building on Hubble's groundbreaking discovery of an expanding universe, let's now turn our attention to another monumental piece of evidence that solidified the Big Bang theory: cosmic microwave background radiation. This fascinating phenomenon was first uncovered in the mid-1960s by two American radio astronomers, Arno Penzias and Robert Wilson, whose accidental discovery completely transformed our understanding of the early universe. At the time, Penzias and Wilson were working with a sensitive microwave detector at Bell Labs, searching for faint signals in space. However, they encountered an unexpected hurdle: a persistent, low-level noise that seemed to come from every direction in the sky. Despite their best efforts to eliminate potential sources of interference, including cleaning bird droppings from their antenna, the mysterious signal remained. It wasn't until they collaborated with theoretical physicists who had predicted the existence of leftover radiation from the Big Bang that the significance of their findings became clear. This radiation, known as cosmic microwave background radiation, represents the oldest light in the universe, dating back to just 380,000 years after the Big Bang. What makes it so extraordinary is its incredible uniformity across the entire sky, a testament to the young universe's smooth and homogeneous state. Tiny fluctuations in temperature, which later seeded galaxies and cosmic structures, were only identified through advanced measurements decades later. The discovery of cosmic microwave background radiation was a turning point in cosmology, providing direct observational support for the Big Bang theory. For their pioneering work, Penzias and Wilson were awarded the Nobel Prize in Physics in 1978, cementing their legacy in the annals of scientific history. Their findings demonstrated that the universe wasn't just expanding, but that it had a definitive beginning, a hot, dense state that evolved over billions of years into the vast cosmos we see today. With this discovery, the Big Bang theory moved from a theoretical framework to a cornerstone of modern cosmology, setting the stage for further revelations about our cosmic origins. Next, we'll delve into the role of light element abundances in confirming the theory's predictions. Shifting our focus from cosmic microwave background radiation, let's explore another crucial piece of evidence supporting the Big Bang theory: light element abundances. These elements, primarily helium and deuterium, play a vital role in confirming the conditions of the early universe. Through a process known as Big Bang nucleosynthesis, the first atomic nuclei were formed mere minutes after the universe's birth. During this fleeting era, the cosmos was incredibly hot and dense, allowing protons and neutrons to fuse together to create light elements. Helium, in particular, was produced in abundance alongside trace amounts of deuterium and lithium. The ratios of these elements provide a window into the conditions of the universe when it was just a few minutes old. Remarkably, the observed abundances of helium and deuterium align almost perfectly with theoretical predictions, offering some of the most compelling evidence for the Big Bang theory. To understand the significance of these ratios, imagine a cosmic recipe. For every 100 hydrogen atoms, there are approximately 24 helium atoms. This helium to hydrogen ratio is remarkably consistent across the universe, from distant galaxies to nearby star-forming regions. Deuterium, a less common isotope of hydrogen, is even more telling. Since it is easily destroyed in stars, its presence today must come directly from the Big Bang, acting as a pristine record of the early universe. This process of Big Bang nucleosynthesis not only reveals the universe's primordial conditions, but also highlights the delicate balance of forces that governed its infancy. It shows how the first elements emerged in a predictable pattern, setting the stage for the more complex chemistry that would later arise in stars and galaxies. By studying these isotopic ratios, scientists gain insights into the density of baryonic matter in the universe, linking the early moments of creation to the cosmos we observe today. Through advanced simulations and measurements, the evidence from light element abundances solidifies our understanding of the universe's origins. These seemingly simple elements tell a profound story of the universe's beginnings, enriching our knowledge of how everything we see today came to be. As we continue our journey, let's now explore the next layer of discovery: cosmic inflation and its dramatic implications for the universe's structure. Shifting our gaze from the primordial elements, let's journey into one of the most mind-bending chapters of cosmic history: the inflationary period. Proposed by physicist Alan Guth in the early 1980s, this revolutionary theory explains how the universe underwent an unimaginably rapid expansion in the tiniest fraction of a second after the Big Bang. Picture this: in less than 1/10 billionth of a second, the cosmos grew from smaller than a proton to about the size of a grapefruit. That might sound like science fiction, but it's a vital piece of the puzzle that helps us understand the universe's shape, structure, and even its uniformity. The concept of inflation elegantly solves some of the biggest mysteries in cosmology. For instance, why is the universe so astonishingly flat? In simple terms, flatness means that the geometry of space closely matches the predictions of Einstein's equations, where parallel lines never meet, and the angles of a triangle always add up to 180 degrees. Inflation provides a natural explanation for this by stretching the fabric of space so profoundly that any initial curvature becomes negligible, much like how the surface of a balloon appears flat when inflated to a large enough size. Inflation also addresses the universe's remarkable homogeneity or smoothness. When we look at the cosmic microwave background, the leftover glow from the Big Bang, we find that its temperature is almost identical in every direction, varying by only 1 part in 100,000. This uniformity might seem obvious, but it creates a paradox known as the horizon problem. Regions of the universe that appear causally disconnected today must have somehow been in contact in the past to achieve such harmony. Inflation solves this by suggesting that these regions were once much closer together, allowing them to equilibrate before being driven apart by the exponential expansion. What makes inflation even more fascinating is its implications for the larger picture of the cosmos. It hints at the existence of quantum fluctuations, tiny ripples in the fabric of space-time, that grew during inflation to become the seeds of galaxies and cosmic structures. Without inflation, the universe would lack the small imperfections needed for gravity to sculpt matter into the stars and galaxies we see today. This groundbreaking theory has transformed our understanding of the universe's infancy, offering solutions to some of its deepest puzzles while opening doors to new questions about its ultimate nature. As we continue our exploration, the next discovery awaits, delving deeper into the secrets written in the stars. Building on the incredible implications of inflation, let's now uncover one of the most fascinating cosmic processes: how quantum fluctuations during the inflationary period laid the groundwork for the magnificent structures we see in the universe today. Imagine the early universe as a vast cosmic garden. Just as a gardener plants tiny seeds that eventually grow into towering trees and vibrant flowers, the universe was sown with microscopic fluctuations that would blossom into galaxies, galaxy clusters, and even the largest cosmic filaments. Quantum fluctuations are essentially tiny disturbances in the fabric of space-time, born from the inherent uncertainty of quantum mechanics. During the brief but explosive phase of inflation, these minuscule ripples were stretched and amplified, transforming from quantum-level perturbations into much larger density fluctuations. These fluctuations acted like gentle variations in the cosmic blueprint, dictating where matter would clump together under gravity and where vast voids would form. To understand this process better, picture a smooth sheet of paper that suddenly develops tiny wrinkles as it's stretched. These imperfections, though barely noticeable at first, become more pronounced as the sheet continues to expand. Similarly, the quantum fluctuations expanded exponentially during inflation, creating regions of slightly higher or lower density. These density differences acted as gravitational attractors, pulling surrounding matter toward them over billions of years. This gradual accumulation of matter eventually gave rise to the stars, galaxies, and clusters we observe today. The evidence for this incredible process can be found in the cosmic microwave background radiation, where tiny temperature variations map out the primordial density fluctuations. These fluctuations, amounting to only 1 part in 100,000, correspond precisely to what we see in the large-scale structure of the universe. Through the lens of inflation, these seemingly random variations become a cosmic blueprint, revealing the seeds of structure planted in the universe's infancy. This remarkable story not only deepens our understanding of the universe's origins, but also highlights the profound interconnectedness of the smallest quantum phenomena with the largest cosmic structures. As we continue our cosmic journey, the next discovery will further illuminate the intricate dance of forces that shaped our universe. Let's now delve into one of the most puzzling questions that inflation elegantly resolves: the horizon problem. At first glance, the uniformity of the cosmic microwave background radiation seems almost magical. How is it that regions of the universe separated by vast distances appear to have the same temperature, even though they've never had the chance to exchange energy or information? This mystery arises because light, the fastest traveler in the universe, hasn't had enough time to bridge the gap between these distant regions since the Big Bang. In other words, these regions are causally disconnected, meaning no physical process could have allowed them to reach thermal equilibrium. Here's where inflation steps in with its extraordinary explanation. During the brief but incredible period of exponential expansion, the universe grew from unimaginably small to vastly larger scales in an instant. This rapid expansion pushed regions that were initially close together far apart to the point where they appear disconnected today. However, before inflation began, these regions were in direct contact, sharing energy and achieving a uniform temperature. As inflation stretched the universe, it preserved this uniformity, effectively solving the horizon problem. To visualize this, imagine a balloon with closely spaced dots drawn on its surface. As the balloon inflates rapidly, the dots move farther apart, but the pattern remains consistent. Similarly, the universe's initial uniformity was preserved despite the enormous distances created by inflation. This process ensures that even the most distant regions of the universe share the same properties, explaining the remarkable consistency of the cosmic microwave background radiation. Understanding the horizon problem not only highlights the brilliance of inflation, but also underscores how the smallest details of the early universe hold the keys to explaining its grandest features. As we explore further, the next discovery will reveal another fascinating aspect of the universe's architecture. Let's now shift our focus to another profound puzzle of the cosmos, the flatness problem. This mystery revolves around the universe's geometry, which, according to observations, is remarkably close to being flat. To understand this, we must first explore the concept of critical density, a term derived from Einstein's field equations of general relativity. Critical density represents the exact amount of matter and energy needed for the universe to achieve a perfectly flat geometry, where space curves neither inward nor outward. Here's the challenge: if the density of the universe deviated even slightly from this critical value in its early stages, the curvature would have grown exponentially over time, resulting in either a closed universe that collapses inward or an open one that stretches infinitely. However, observations reveal that the universe is astonishingly close to being flat, which raises the question: how did it maintain such precise balance? This is where inflation steps in once again with an elegant solution. During the brief yet colossal period of exponential expansion, inflation stretched the universe so vastly that any initial curvature, no matter how extreme, was effectively flattened. Think of it like inflating a balloon to an enormous size. Even the smallest imperfections on its surface become indistinguishable as the balloon expands. Similarly, inflation erased the early universe's curvature, leaving behind the nearly flat geometry we observe today. The significance of this lies in the fact that inflation provides a natural explanation for the universe's uncanny flatness, bypassing the need for fine-tuned initial conditions. It tells us that the universe didn't require an improbable precision in its early density to achieve its current state. Instead, inflation dynamically adjusted the geometry, solving the flatness problem with remarkable simplicity. This revelation highlights the power of inflation as a framework for understanding not just the why, but also the how of the universe's architecture. As we continue this journey, the next discovery will take us deeper into the intricacies of cosmic structure and its origins. Discovery 9, Galaxy Formation and Large-Scale Structure, begins with a fascinating exploration of how galaxies came into existence and how they shaped the universe's cosmic web. Let's dive deeper into this intricate process, starting with the crucial role of dark matter halos. These invisible structures, made up of mysterious particles that don't emit light but exert gravitational pull, acted as cosmic scaffolding during the universe's infancy. Without them, the formation of galaxies as we know them today might not have been possible. In the early universe, tiny fluctuations in the distribution of dark matter provided the seeds for gravitational collapse. As dark matter clumped together under its own gravity, it created dense regions that attracted ordinary matter, gas, dust, and other materials. Over billions of years, this attraction led to the birth of stars and galaxies within these vast halos. Essentially, dark matter created the framework upon which galaxies could grow and thrive. To better visualize this process, scientists have relied on powerful computer simulations such as the Millennium simulation. These groundbreaking models allow researchers to recreate the universe's evolution from its initial conditions to the present day. By simulating the interplay between dark matter and ordinary matter, these simulations reveal stunning cosmic structures like galaxy filaments and voids. Filaments form long, thread-like chains where galaxies cluster together, while voids represent enormous empty spaces devoid of significant matter. Together, they create the cosmic web, an awe-inspiring pattern that tells the story of the universe's structure on the largest scales. This interplay between gravity, dark matter, and the formation of galaxies is essential to understanding not only how galaxies came to be, but also their arrangement across the cosmos. It paints a picture of a universe far more complex and interconnected than we ever imagined. And with each new simulation and observation, we get closer to unraveling its mysteries. But there's still much more to learn, as the next discovery will show, taking us further into the secrets of the universe's architecture. Discovery 10, Dark Energy's Role in Cosmic Expansion, begins with a groundbreaking revelation that reshaped our understanding of the universe. While the Big Bang and cosmic inflation set the stage for the universe's initial expansion, another mysterious force has taken center stage in its ongoing journey: dark energy. This enigmatic phenomenon is responsible for the universe's accelerated expansion, a discovery that has left scientists both intrigued and puzzled. To grasp the significance of dark energy, we must look back to the late 1990s when two independent teams of astronomers made a startling observation. They were studying distant Type Ia supernova, a specific kind of stellar explosion that acts as a standard candle for measuring cosmic distances. These explosions occur when a white dwarf star in a binary system accumulates enough material to reach a critical mass, triggering a thermonuclear detonation. Because Type Ia supernova consistently release the same amount of light, their apparent brightness can be used to calculate their distance from Earth. What the researchers found was astonishing. Instead of slowing down due to the gravitational pull of matter, the universe's expansion was speeding up. This acceleration contradicted the prevailing belief that gravity would eventually slow or even reverse the expansion. The only explanation was the presence of a repulsive force, dark energy, that counteracts gravity on cosmic scales. Dark energy makes up approximately 70% of the universe's total energy content, yet its nature remains elusive. One popular theory suggests it is tied to the cosmological constant, a term introduced by Albert Einstein in his equations of general relativity. Originally dismissed by Einstein himself, this constant re-emerged as a potential explanation for dark energy's influence on the universe's expansion. The discovery of dark energy not only deepens our understanding of the universe's past, but also offers crucial insights into its future. As the universe continues to expand faster, galaxies will drift farther apart, and the night sky may one day appear eerily empty. Yet, the role of dark energy in this cosmic drama remains one of the greatest mysteries, linking the aftermath of the Big Bang to the infinite possibilities of what lies ahead. Building on the revelations of dark energy, let us now turn our attention to one of the most significant advancements in our understanding of the cosmos, the Wilkinson Microwave Anisotropy Probe, or wmap. Launched in 2001, this remarkable spacecraft took precision cosmology to new heights, offering us an unprecedented glimpse into the early universe. wmap was designed to map the cosmic microwave background radiation, the faint afterglow of the Big Bang, with unprecedented accuracy. By studying the tiny temperature fluctuations in this radiation, scientists could infer crucial details about the universe's composition, age, and structure. These fluctuations, though minuscule, contain a wealth of information, acting as a cosmic blueprint for the universe's history. The findings from wmap revolutionized our understanding of the cosmos. For starters, it pinpointed the universe's age with remarkable precision at approximately 13.7 billion years. Moreover, wmap provided definitive evidence for the universe's composition: roughly 4% ordinary matter, 23% dark matter, and 73% dark energy. This breakdown confirmed earlier theories and laid the foundation for subsequent research. Visualizations of wmap all sky maps revealed a breathtaking panorama of the early universe, showcasing the intricate patterns of temperature variations. These maps not only validated the inflationary theory, but also helped refine our understanding of the universe's geometry. The near-perfect flatness of the universe, a mystery for decades, was finally explained through the insights gained from wmap data. Beyond its scientific achievements, wmap legacy lies in its ability to connect the dots between the Big Bang, cosmic inflation, and the universe's present state. It bridged the gap between theory and observation, paving the way for future missions like the Planck satellite. As we delve deeper into the mysteries of the universe, the contributions of wmap remain a cornerstone of modern cosmology, guiding us toward answers to the most profound questions about our cosmic origins. Following the groundbreaking achievements of wmap, the next chapter in our journey through cosmic discovery brings us to the Planck satellite, a mission that took precision cosmology to an even higher level. Launched in 2009, Planck was designed to build upon wmap foundation, delivering the most detailed and accurate maps of the cosmic microwave background radiation ever created. With its advanced sensors and groundbreaking technology, Planck provided scientists with an unparalleled view of the early universe, offering insights that were sharper, more refined, and more informative than ever before. One of the most significant contributions of the Planck satellite was its ability to produce high-resolution maps of the temperature fluctuations in the CMB. These fluctuations, though subtle, hold the key to understanding the universe's origins, composition, and evolution. By measuring these variations with unprecedented accuracy, Planck allowed researchers to refine their understanding of the universe's fundamental parameters. For example, the data collected from Planck revised the universe's age slightly, settling on approximately 13.8 billion years. Additionally, it refined the cosmic inventory, showing that dark matter makes up about 26% of the universe, while dark energy accounts for 69%, leaving ordinary matter at just about 4.9%. Another crucial aspect of Planck's findings was its ability to distinguish subtle differences from the data collected by wmap. While wmap maps were groundbreaking, Planck's higher resolution exposed new details such as smaller temperature variations and more intricate patterns in the CMB. These patterns helped refine our understanding of the universe's geometry, confirming its near-perfect flatness and strengthening the case for cosmic inflation. Animations comparing the maps produced by wmap and Planck reveal these differences clearly, showing how Planck's sharper view brought the universe's blueprint into sharper focus. In summary, the Planck satellite's contributions marked a major leap forward in our understanding of the cosmos. building on the successes of wmap while pushing the boundaries of what we know about the universe's earliest moments. Its high-resolution maps and refined data laid the groundwork for future discoveries, continuing the legacy of precision cosmology and deepening our appreciation of the wonders of the cosmos. Moving on from the remarkable contributions of the Planck satellite, let's delve into another profound aspect of cosmic exploration: the search for gravitational waves as echoes of inflation. This intriguing concept suggests that during the universe's rapid inflationary phase, violent fluctuations in the fabric of space-time produced gravitational waves. These waves, much like ripples in a pond, left imprints in the cosmic microwave background radiation, specifically in the form of something called B-mode polarization patterns. B-mode polarization is a type of twisted or swirly pattern that can be detected in the CMB. Unlike the more straightforward temperature fluctuations we previously discussed, these patterns are subtle and require highly precise instruments to observe. They are considered one of the most direct pieces of evidence for cosmic inflation, acting as a sort of fossil record of the universe's early moments. The detection of these patterns would provide powerful confirmation of the inflationary model, while offering insights into the exact mechanism driving this incredible expansion. One of the most notable efforts in this field was the BICEP-2 experiment conducted at the South Pole. In 2014, the BICEP-2 team announced they had detected B-mode polarization patterns in the CMB, sparking immense excitement in the scientific community. However, this discovery soon became controversial when it was revealed that the observed signal might have been influenced by dust in our own Milky Way galaxy. This revelation highlighted the immense challenges in distinguishing between signals from the early universe and local interstellar phenomena. Despite this setback, the quest continues. Upcoming experiments like the third iteration of BICEP and the next-generation CMB-S4 observatory aim to refine our measurements further, ensuring that any detected B-mode polarization genuinely reflects the primordial gravitational waves. If confirmed, these discoveries could revolutionize our understanding of the universe's beginnings, offering unprecedented insights into the nature of cosmic inflation and the fundamental laws governing the cosmos. Shifting our focus from the hunt for gravitational waves, let us now explore one of the most mind-bending ideas that has emerged from the study of cosmic inflation: the theory of eternal inflation and its profound implications for the existence of multiple universes. This concept suggests that inflation, rather than being a single event confined to our universe, is an ongoing process that never truly ends. In some regions of space-time, inflation stops, allowing universes like ours to form. But in other regions, it continues indefinitely, giving rise to what scientists call a multiverse, a vast ensemble of separate and distinct universes, each with its own unique set of physical laws. Imagine a cosmic bubble bath where each bubble represents a distinct universe, potentially with different properties and constants. In this scenario, our universe is just one of countless bubbles floating within a much larger cosmic ocean. While this idea may sound like science fiction, it arises naturally from the mathematics of inflationary theory. If inflation is indeed eternal, then it becomes almost inevitable that other universes exist beyond the boundaries of our own. Of course, this notion raises more questions than it answers. How can we test such a hypothesis? Can we ever observe evidence of other universes? These are some of the most challenging and exciting questions facing cosmologists today. The idea of a multiverse challenges our fundamental understanding of reality and forces us to reconsider the uniqueness of our universe. Though speculative, the theory of eternal inflation offers a tantalizing glimpse into the infinite possibilities of existence, sparking the imagination and inspiring new avenues of research. As technology advances and our understanding deepens, perhaps one day we will uncover clues that confirm or refute the breathtaking possibility of a multiverse. Transitioning from the mind-expanding possibilities of a multiverse, let us now zoom in on the vast, intricate structure of our own universe and delve into one of the most breathtaking discoveries in cosmology, the cosmic web. This term describes the stunning large-scale organization of matter in the universe, revealing a network of filaments, walls, and voids that form an awe-inspiring cosmic tapestry. Imagine the universe as a colossal cosmic spider web, with galaxies strung along vast threads of matter, separated by enormous empty spaces called voids. These filaments, made up of both visible galaxies and invisible dark matter, span billions of light years and connect regions of the universe in a complex three-dimensional web. This structure arises naturally from the gravitational pull of dark matter, which acts as a scaffold for galaxies and clusters to form around. As matter clumps together, it creates dense walls and filamentary structures, leaving behind vast, mostly empty voids where very few galaxies reside. The cosmic web is not just a beautiful pattern, it holds critical clues about the universe's history and evolution. By studying its intricate network, scientists can trace how tiny fluctuations in the early universe grew into the massive structures we see today. The way galaxies align and cluster along these filaments can help us understand dark matter's role in shaping the universe and test theories about how cosmic inflation influenced the distribution of matter. What makes the cosmic web even more fascinating is its sheer scale. Filaments can stretch across hundreds of millions of light years, while voids can reach sizes of over 1 billion light years across. Yet despite these immense dimensions, the web maintains an almost delicate balance, revealing the underlying forces that govern the cosmos. Through cutting-edge simulations and observations, we continue to uncover the secrets of this extraordinary structure, enhancing our understanding of the universe's architecture and its fundamental nature. Shifting our focus from the cosmic web, let us now journey back to the infancy of the universe and uncover the origin of the first stars and galaxies. These early cosmic pioneers, known as population Roman III stars, played a pivotal role in shaping the universe as we know it today. Born in an era when the cosmos was still a dark, cold place, these ancient stars transformed the universe by igniting the first sparks of light and initiating a process called reionization. Population Roman III stars were the first generation of stars, forming from the primordial hydrogen and helium gas that filled the early universe. Unlike the stars we see today, these giants were likely much larger, with masses tens to hundreds of times that of our Sun. Their immense size meant they burned through their nuclear fuel at an extraordinary rate, living only a few million years before ending their lives in spectacular supernova explosions. These explosions scattered heavy elements like carbon and oxygen into the cosmos, enriching the interstellar medium and paving the way for the formation of subsequent generations of stars. The emergence of these first stars also triggered a fundamental transformation of the cosmic environment. During the so-called Dark Ages, the universe was filled with neutral hydrogen gas. As population Roman III stars began to shine, their intense ultraviolet radiation ionized this hydrogen, splitting it into free protons and electrons. This process, known as reionization, fundamentally altered the universe's transparency, allowing light to travel freely for the first time in millions of years. In parallel with this star formation, the first galaxies started to take shape. These primordial galaxies were much smaller and less structured than the grand spirals and ellipticals we observe today. They formed from the gravitational collapse of dark matter halos, which acted as cosmic scaffolds, pulling in surrounding gas and stars. Over time, these early galaxies grew through mergers and accretion, gradually evolving into the majestic cosmic structures we see scattered across the night sky. Understanding the formation of the first stars and galaxies requires advanced simulations and observations. Cutting-edge telescopes like the James Webb Space Telescope are now able to peer deep into the universe's past, capturing images of these ancient cosmic objects. Animations of star formation and galaxy evolution help visualize this complex process, showing how swirling clouds of gas collapse under gravity, ignite nuclear fusion, and then scatter their remnants across the cosmos. Through these efforts, we continue to unravel the mysteries of the universe's earliest stars and galaxies, further illuminating the cosmic story of creation. Black hole seeds in the early universe represent one of the most intriguing possibilities arising from our understanding of cosmic evolution. Just as the first stars and galaxies began to take shape, another mysterious phenomenon may have been unfolding, a type of black hole known as primordial black holes. Unlike the stellar black holes we are familiar with today, which form from the collapse of massive stars, primordial black holes could have formed much earlier, shortly after the Big Bang, during an era when the universe was still incredibly dense and hot. To understand how these black holes might have formed, let's delve into the conditions of the early universe. In the moments following the Big Bang, tiny fluctuations in density, amplified by cosmic inflation, could have created regions of space that were dense enough to collapse under their own gravity. These collapses, happening in fractions of a second, would have given birth to black holes that spanned a wide range of sizes, from as small as an atom to potentially weighing as much as a mountain or even larger. What makes primordial black holes particularly fascinating is their potential role as seeds for the supermassive black holes that now reside at the centers of galaxies. If these ancient black holes indeed existed, they could have influenced cosmic evolution in profound ways. For instance, their gravitational pull might have helped guide the formation of the first galaxies by attracting nearby gas and matter, acting as cosmic anchors. Additionally, interactions between primordial black holes and surrounding matter could have contributed to the creation of heavy elements during the early universe, further enriching the interstellar medium. While we have yet to directly observe primordial black holes, researchers continue to explore their potential impact on cosmic evolution. Cutting-edge observatories and experiments such as gravitational wave detectors offer promising avenues for detecting these elusive objects. By studying their hypothetical presence, we gain deeper insights into the universe's earliest moments and the forces that shaped it. As our tools grow more sophisticated, we edge closer to uncovering whether these ancient black holes truly existed and what role they played in the cosmic narrative. Shifting our focus from the enigmatic primordial black holes, let's now explore another fascinating contender in the cosmic mystery of dark matter actions. These hypothetical particles have captured the imagination of physicists as potential dark matter candidates, and their connection to cosmic inflation makes them even more intriguing. Actions were first proposed to solve a puzzle in particle physics known as the strong CP problem, but their properties also make them excellent candidates for dark matter. Unlike the familiar particles that make up ordinary matter, actions are theorized to be extraordinarily light, yet they exist in vast numbers. Their existence, if confirmed, could explain why galaxies rotate faster than expected, hinting at the presence of unseen mass, dark matter. What links actions to cosmic inflation? During the brief but incredible expansion of the universe in the first fractions of a second, the conditions were just right for particles like actions to be created. Inflationary models suggest that quantum fluctuations during this epoch could have produced actions in sufficient abundance to account for the missing dark matter in the universe. This connection between actions and cosmic inflation offers a tantalizing glimpse into the early universe's forces and particles. But how do scientists search for these elusive particles? Currently, cutting-edge experiments are underway to detect actions. One approach involves using specialized devices, such as microwave cavities, to convert actions into detectable photons under the influence of strong magnetic fields. Another promising method is the use of haloscopes, which are designed to capture the minuscule signals produced by actions interacting with matter. These experiments require extreme precision and sensitivity, pushing the boundaries of modern technology. While the existence of actions remains unproven, the possibility that they might compose a significant portion of dark matter makes their discovery a top priority in astrophysics. As our understanding of cosmic inflation deepens, the search for actions grows ever more relevant, offering clues not only about dark matter, but also about the universe's fundamental forces in its infancy. Transitioning from the intriguing quest for actions, let us now turn our attention to another cornerstone of cosmology, baryon acoustic oscillations, or BAO. These oscillations serve as a cosmic standard ruler, allowing scientists to measure vast distances across the universe with remarkable precision. Imagine the early universe as a dense, hot plasma where pressure waves, essentially sound waves, propagated through the cosmos. These waves created subtle density fluctuations in the distribution of matter, leaving imprints that persist to this day in the way galaxies cluster together. To understand BAO, think of ripples spreading across a pond when you drop a stone. Just as those ripples carry information about the disturbance that caused them, the baryon acoustic oscillations encode details about the conditions of the early universe. As the universe expanded and cooled, the sound waves froze into place, forming a characteristic scale of about 450 million light-years today. This scale acts as a cosmic benchmark, enabling astronomers to map the large-scale structure of the universe. How do scientists detect these oscillations? By analyzing the distribution of galaxies in the night sky. The clustering pattern of galaxies exhibits a slight preference for separations corresponding to the BAO scale, like a faint watermark woven into the fabric of cosmic structure. Advanced surveys such as the Sloan Digital Sky Survey have revealed these patterns with incredible clarity, providing critical evidence for the expansion history of the universe. BAO not only helps measure cosmic distances but also sheds light on dark energy's role in accelerating that expansion. By comparing BAO measurements at different epochs of the universe's history, researchers can piece together how dark energy has influenced the cosmos over time. In this way, baryon acoustic oscillations bridge the gap between the Big Bang and the current state of the universe, offering profound insights into its evolution and ultimate fate. Moving forward, let us delve into one of the most pivotal moments in the early universe's history, the epoch of recombination. This era marks a transformation that allowed the universe to become transparent, setting the stage for the cosmic microwave background radiation we observe today. Imagine the universe just 380,000 years after the Big Bang. At this point, it was an incredibly hot and dense plasma, where protons and electrons were constantly colliding, unable to combine due to the intense energy. However, as the universe expanded, it gradually cooled, allowing a significant change to occur. At temperatures of roughly 3000 Kelvin, the conditions became just right for electrons and protons to combine, forming neutral hydrogen atoms. This process, known as recombination, was not instantaneous but rather an extended period during which the universe transitioned from an opaque state to one of transparency. What happened next was nothing short of extraordinary. With the formation of neutral atoms, photons previously trapped in the plasma were suddenly free to travel unimpeded through space. This liberation of light marked the first time the universe became transparent, creating a cosmic snapshot that we now detect as the cosmic microwave background radiation. This radiation, cooled over billions of years, carries the imprints of the universe's earliest moments, offering invaluable insights into the conditions of the early cosmos. The epoch of recombination is significant not only because it produced the cosmic microwave background, but also because it allowed for the formation of the large-scale structures we see today. Neutral atoms laid the groundwork for gravity to take over, pulling matter together and eventually forming stars, galaxies, and the vast cosmic web. This moment in the universe's history serves as a bridge between its extremely hot and dense beginnings and the relatively cool, structured universe we inhabit now. Understanding recombination is crucial for piecing together the entire cosmic timeline, giving us a clearer picture of how everything we know came to be. Shifting our focus now to another fascinating aspect of the early universe, let's explore the intriguing role of neutrinos. These elusive particles, often called ghost particles, played a crucial part in shaping the cosmos during its infancy. To understand their significance, we need to delve into the timeline of the universe's first moments and how neutrinos interacted with the environment around them. As the universe expanded and cooled roughly 1 second after the Big Bang, neutrinos began to decouple from the hot plasma of particles. This decoupling marked the point where neutrinos stopped interacting with other particles and started traveling freely through space. Unlike photons, which remained trapped in the plasma for hundreds of thousands of years, neutrinos became the universe's earliest unbound travelers. Their release left a faint imprint on the cosmos, providing astronomers with a unique window into the universe's first moments. Neutrinos also played a vital role in Big Bang nucleosynthesis, the process by which light elements like hydrogen, helium, and lithium were formed. During this period, the density and temperature of the universe dictated the types of interactions that could occur between particles. Neutrinos influenced the balance of neutrons and protons, affecting the abundance of these elements. Their presence altered the rate at which neutrons could combine with protons, shaping the final proportions of light elements observed today. Beyond their impact on nucleosynthesis, neutrinos contributed to the formation of cosmic structures. Since they were among the first free-moving particles in the universe, they influenced the distribution of matter on large scales. As gravity began to pull matter together, the presence of neutrinos affected how clusters of galaxies and other structures formed. Their subtle influence can still be detected in the cosmic microwave background radiation, carrying traces of their movements billions of years ago. Despite their tiny mass and reluctance to interact, neutrinos remain a key piece of the cosmic puzzle. Their study continues to reveal new insights into the universe's origins and evolution, offering glimpses into the most fundamental processes of the early cosmos. By examining how neutrinos behaved during the decoupling phase, scientists gain invaluable clues about the conditions and dynamics of the early universe. This chapter in cosmic history underscores the interconnectedness of all particles, showing how even the smallest and hardest to detect entities can leave lasting imprints on the grand tapestry of the cosmos. Exploring the future of cosmic inflation research, we turn our attention to the cutting-edge experiments and observatories pushing the boundaries of our understanding. Among the most promising projects is the Cosmic Microwave Background Stage 4, or CMBS-4, an ambitious initiative designed to probe deeper into the mysteries of the early universe. With a network of advanced telescopes strategically placed in some of the world's driest regions, such as Chile's Atacama Desert, CMBS-4 aims to capture the most precise measurements of the cosmic microwave background radiation yet. By analyzing tiny fluctuations in this ancient light, scientists hope to uncover definitive evidence of primordial gravitational waves, which would provide direct insights into the inflationary epoch. Another groundbreaking facility set to revolutionize our understanding is the Simons Observatory, located on the high-altitude grounds of Cerro Toco in Chile. Equipped with state-of-the-art detectors capable of measuring polarization patterns in the CMB, the observatory seeks to detect the elusive B-mode signals predicted by inflationary theory. These signals, if confirmed, would offer a smoking gun for cosmic inflation, reinforcing our current cosmological models while opening new avenues of exploration. Meanwhile, upcoming space-based missions like the LightBird satellite promise to expand our observational capabilities even further. Designed specifically to hunt for the faint traces of inflation, LightBird will provide unparalleled sensitivity and resolution, scanning large portions of the sky for the subtle imprints left by gravitational waves. Working in tandem with ground-based observatories, these missions represent a coordinated global effort to unlock the secrets of the universe's earliest moments. As these projects progress, they not only bring us closer to understanding cosmic inflation, but also highlight the collaborative spirit driving modern astrophysics. By harnessing the power of advanced technology and innovative approaches, researchers are paving the way for groundbreaking discoveries that will undoubtedly reshape our comprehension of the cosmos. The next chapter in this cosmic quest is just beginning, with each new observation bringing us one step closer to deciphering the universe's most profound mysteries. Shifting our focus to one of the most intriguing puzzles in cosmology, let us delve into the cosmic coincidence problem and its profound implications for our understanding of dark energy and inflation. At its core, this problem revolves around an astonishing observation. The present era in the universe's history is unique because the densities of matter and dark energy are remarkably similar. This similarity might seem unremarkable at first glance, but when you consider the vast age of the universe, approximately 13,800,000,000 years, it becomes an extraordinary coincidence. To understand this better, imagine the universe as a marathon. Matter and dark energy are like two runners at different paces. For billions of years, matter dominated the race, shaping the universe through gravity. However, as the universe expanded and thinned out, dark energy, acting as a repulsive force, gradually gained prominence, causing the expansion to accelerate. The cosmic coincidence problem arises because today, at this precise moment in cosmic history, these two forces are neck and neck in their influence. Why does this balance occur now, rather than at some random point in the universe's past or future? This problem raises deeper questions about the nature of dark energy and its connection to cosmic inflation. Both phenomena involve mysterious forces driving the universe's expansion, yet they operate on vastly different scales. Could inflation and dark energy be related? This possibility suggests that the same fundamental physics might govern both the universe's earliest moments and its distant future. The cosmic coincidence problem also challenges our perception of time and scale. It forces us to consider whether we live in a special epoch or if this apparent balance is merely an illusion created by our incomplete understanding of cosmology. As researchers continue to explore this mystery, the cosmic coincidence problem serves as a reminder of how much we still have to learn about the forces shaping our universe. By unraveling its complexities, we may uncover new insights into the intricate dance between matter, dark energy, and the legacy of inflation. Moving forward from the cosmic coincidence problem, let us now turn our attention to one of the most profound questions in cosmology. What is the ultimate fate of the universe? The Big Bang and cosmic inflation not only shaped the universe's beginning but also set the stage for its potential endings. By understanding the forces driving the universe's expansion, particularly the role of dark energy, we can explore several intriguing scenarios for its distant future. One possibility is the Big Freeze, where the universe continues expanding indefinitely. As galaxies drift farther apart and stars burn out, the cosmos will gradually grow colder and darker. Eventually, all matter will dissipate into isolated, inert objects, leaving behind a vast, empty space. This scenario paints a picture of a universe that slowly fades into obscurity, driven by the relentless pull of dark energy. Another intriguing possibility is the Big Rip. In this scenario, the acceleration caused by dark energy increases exponentially over time, eventually tearing apart galaxies, stars, and even atomic structures. The universe would literally rip itself apart, ending in an unimaginably violent finale. This outcome highlights the powerful and potentially destructive nature of dark energy, a force still shrouded in mystery. On the other hand, there is the concept of the Big Crunch. If the universe contains enough matter and energy to eventually halt and reverse its expansion, it could collapse back into an incredibly dense state, much like the conditions before the Big Bang. This idea suggests that the universe's history might be cyclical, with endless iterations of birth and rebirth. Each of these possibilities offers a unique glimpse into the universe's future, yet they all depend on the precise nature of dark energy and the fundamental laws governing cosmic evolution. By continuing to study these forces, scientists hope to uncover the truth about the universe's ultimate destiny. This exploration not only deepens our understanding of the cosmos, but also inspires awe at the sheer scale and complexity of existence. Whether it ends in a freeze, a rip, or perhaps something entirely unexpected, the universe's fate remains one of the greatest mysteries of all time. The ultimate unification of physics lies at the heart of modern scientific exploration, where the quest to harmonize quantum mechanics and general relativity takes center stage. For decades, physicists have grappled with the challenge of merging these two pillars of modern science into a single framework that could explain everything from the smallest particles to the vast expanse of the cosmos. Such a unified theory would not only resolve the mysteries of the Big Bang and cosmic inflation, but also answer some of the most fundamental questions about the nature of reality itself. Among the leading contenders in this grand pursuit is string theory, which suggests that the fundamental building blocks of the universe are not point-like particles but rather tiny, vibrating strings. These strings, according to the theory, can oscillate in different ways, giving rise to the various particles and forces we observe. By providing a framework where gravity naturally emerges alongside the other fundamental forces, string theory offers a tantalizing glimpse into how the universe operates at its most fundamental level. However, the theory remains largely speculative, requiring many dimensions beyond our familiar 3 of space and 1 of time, making it difficult to test experimentally. On the other hand, loop quantum gravity seeks to bridge the gap by focusing directly on the fabric of spacetime itself. This approach quantizes spacetime, treating it as a network of loops that form a kind of quantum lattice. By doing so, it attempts to preserve the insights of general relativity while incorporating quantum principles. In loop quantum gravity, the concept of infinite density at the Big Bang, the singularity problem, is replaced with a bounce, suggesting that our universe could have emerged from a previous one in a cyclical process. Both theories present profound ideas that challenge our current understanding, offering potential explanations for cosmic inflation, the early universe's rapid expansion, and the elusive nature of dark energy and dark matter. While neither has yet provided conclusive evidence, they represent humanity's ambitious effort to decode the universe's deepest secrets. The search for this ultimate unification is not merely academic. It holds the promise of revealing the cosmos's true origins and destiny, tying together the threads of the Big Bang, inflation, and everything that followed. As we continue to explore these possibilities, the journey itself enriches our understanding and fuels our awe for the infinite complexity of existence. Moving forward, let us now explore the specific implications of unifying quantum mechanics and general relativity, particularly in addressing some of the most pressing questions surrounding inflation and the Big Bang. This theoretical convergence not only holds the potential to explain the universe's earliest moments, but could also unravel the mechanisms driving cosmic inflation and the behavior of the universe at the smallest scales. One of the key puzzles this unification could solve is the nature of the inflaton field, the hypothetical field thought to drive cosmic inflation. If we can marry quantum mechanics and general relativity, we may gain deeper insights into what this field actually is and how it operates. Current theories suggest that the inflaton field existed in a high-energy state just after the Big Bang, causing the universe to expand exponentially before settling into a lower energy state. However, understanding its exact properties and how it interacts with other fundamental forces remains elusive. a unified theory could provide the missing pieces, offering a clearer picture of how this field fits into the grand cosmic puzzle. Additionally, the singularity problem at the heart of the Big Bang could find resolution through unification. General relativity predicts an infinitely dense point marking the universe's origin, but quantum mechanics suggests that such infinite densities are impossible. By reconciling these two frameworks, we might replace the singularity with a more manageable concept, one that avoids the paradoxes associated with infinite conditions. For instance, loop quantum gravity's bounce scenario offers a tantalizing alternative, suggesting that the universe's beginning might not be a true beginning but rather a transition from a preceding phase. The implications extend further into the realm of dark energy and dark matter. A unified theory could help explain why these mysterious components dominate the universe's composition, influencing its evolution and structure. Dark energy, responsible for the universe's accelerated expansion, might emerge more naturally from a unified framework, potentially revealing its origin and role in cosmic inflation. Similarly, dark matter, which interacts primarily through gravity, could find its true nature illuminated by the same principles that govern both quantum mechanics and general relativity. In essence, unification carries profound potential to bridge gaps in our understanding, opening new avenues for interpreting the Big Bang, cosmic inflation, and the universe's fundamental makeup. This journey into the heart of reality promises not only to refine our theories but also to deepen our connection to the cosmos, answering questions that have intrigued humanity for centuries. Building on the theoretical framework of unification, let us now turn our attention to the groundbreaking experiments and observations that could provide concrete evidence for these advanced concepts. The quest to unite quantum mechanics and general relativity is not just theoretical. It relies heavily on cutting-edge technology and innovative research. Among the most promising avenues for discovery are gravitational wave detection and high-energy particle collisions, which offer unique insights into the extreme conditions of the early universe. Gravitational wave observatories such as LIGO and Virgo have already revolutionized our understanding of cosmic events. These instruments detect ripples in space-time caused by cataclysmic occurrences like black hole mergers and neutron star collisions. If we can refine these technologies further, they might capture signatures from the universe's earliest moments, potentially revealing traces of the inflattened field or even quantum gravitational effects. Imagine a scenario where gravitational waves act as a cosmic time machine, allowing us to peer back to nearly the moment of the Big Bang itself. High-energy particle accelerators like the Large Hadron Collider offer another crucial pathway. By recreating the conditions of the early universe in controlled environments, scientists hope to uncover the fundamental particles and forces that govern reality. These experiments could reveal new particles or interactions that bridge the gap between quantum mechanics and general relativity, perhaps even shedding light on dark matter and dark energy. For instance, the elusive graviton, the hypothetical particle associated with gravity, could make its first appearance in such experiments, providing direct evidence for quantum gravity. Beyond these monumental efforts, future observatories like CMBS-4 and the upcoming space missions aim to enhance our understanding of cosmic inflation through detailed studies of the cosmic microwave background radiation. These projects could detect subtle patterns such as B-mode polarization, which would offer smoking gun evidence for inflation and the conditions during the universe's infancy. Taken together, these experimental endeavors represent humanity's bold attempt to decode the cosmos. Each discovery brings us closer to realizing the ultimate unification of physics, transforming abstract theories into tangible truths. Exploring the philosophical implications of a unified theory, we uncover profound questions about humanity's place in the cosmos and the nature of reality itself. Beyond the technical advancements and experimental breakthroughs, A successful unification of quantum mechanics and general relativity would redefine our understanding of existence on the most fundamental level. Imagine a framework that seamlessly connects the smallest particles to the vast expanse of the universe, revealing a web of interconnectedness that transcends traditional scientific boundaries. Such a theory would challenge deeply ingrained assumptions about space, time, and causality. For centuries, humanity has viewed the universe through the lens of classical physics, where objects exist independently and events unfold sequentially. However, the quantum realm introduces concepts like entanglement and superposition, which defy these intuitive notions. A unifying framework would reconcile these seemingly contradictory perspectives, offering new ways to think about the nature of reality. Moreover, a unified theory could reshape our understanding of consciousness and free will. If the universe operates according to a set of underlying principles that govern all phenomena from subatomic particles to galaxies, what does this mean for human agency? Are our choices predetermined by the laws of physics, or does quantum uncertainty leave room for genuine freedom? These questions, once purely philosophical, may find answers, or at least new dimensions of inquiry, in the context of a fully realized theory of everything. On a broader scale, such a breakthrough would transform our relationship with the cosmos. Humanity's journey to understand the universe has always been intertwined with our search for meaning. From ancient myths to modern science, we seek to make sense of our origins and purpose. A unified theory would provide a comprehensive narrative of existence, offering insights not only into how the universe works, but also why it exists at all. This could inspire a new era of philosophical exploration, bridging the gap between science and the timeless questions of existence. Ultimately, the pursuit of a unified theory is more than a scientific endeavor, it is a deeply human one. By striving to understand the universe, we come to know ourselves better and our place within the grand tapestry of reality. As we move closer to this ultimate understanding, we may find that the most profound discoveries lie not in the equations themselves, but in the way they reshape our perspective on life, the cosmos, and everything in between. In summary, the journey through these 25 incredible discoveries about the Big Bang and cosmic inflation reveals how far our understanding of the universe has come. From Edwin Hubble's groundbreaking realization that the universe is expanding to the detection of gravitational waves echoing the universe's earliest moments, each discovery adds a vital piece to the cosmic puzzle. Together, they paint a picture of a universe born from an unimaginably hot and dense state, expanding and evolving into the vast and complex reality we observe today. The role of cosmic inflation in smoothing out the universe's irregularities and the evidence provided by cosmic microwave background radiation stand as testament to the power of scientific inquiry. These findings not only deepen our knowledge of the physical processes governing the cosmos, but also challenge us to rethink fundamental questions about existence. The search for dark matter candidates like actions and the exploration of neutrinos in the early universe continue to push the boundaries of our understanding, bridging gaps in our knowledge and opening new avenues of research. As we contemplate the philosophical implications of unifying quantum mechanics and general relativity, it becomes clear that the pursuit of knowledge is a deeply human endeavor. Our quest to understand the universe's origins and evolution mirrors our broader search for meaning and purpose. This journey transforms us, reshaping our perspective on life and our place within the cosmos. We invite you to join us in this ongoing exploration of the universe's mysteries. Share your thoughts in the comments below. What discovery excites you the most? And don't forget to hit the subscribe button and enable notifications so you never miss an update on our quest to uncover the secrets of the cosmos. There's always more to discover, and together we can continue unraveling the mysteries of space.